Have you ever stared up at the night sky and wondered what secrets the universe is hiding from us? Beyond the twinkling stars and familiar constellations lies a cosmic playground of mysteries so strange they defy everything we think we know. Picture this: a planet where it rains molten glass sideways, or a black hole with a gravitational pull so intense it distorts time itself. These aren't scenes from a sci-fi movie. They're real, mind-bending phenomena happening right now in the vast expanse of space. And today, we're diving deep into 30 of the most shocking, awe-inspiring facts about our universe that will leave you questioning reality. Think you know space? Think again. Even scientists are constantly stunned by new discoveries that rewrite the rules of physics and challenge our understanding of existence. Did you know there's a cloud of alcohol floating in the depths of the Milky Way, or that a single teaspoon of a neutron star weighs as much as a mountain? The cosmos is brimming with wonders that sound like pure fantasy, yet they're undeniably real. From rogue planets wandering alone in the darkness to galaxies colliding in a dance of cosmic destruction, the universe operates on a scale so grand it humbles even the brightest mind. This journey isn't just about facts, it's about awakening that childlike wonder we all once had when we first looked up at the stars. Each revelation in this video peels back another layer of the universe's infinite mysteries, revealing just how bizarre, beautiful, and utterly unpredictable it all is. So buckle up, because by the time we're done, you'll never see the night sky the same way again. Ready to have your mind blown? Let's begin. The moon may seem like a constant fixture in our night sky, but it's actually playing a slow game of cosmic tug-of-war with Earth. Right now, it's drifting away from us at roughly the speed your fingernails grow, about 1.5 inches every year. This might sound insignificant, but over millions of years, those tiny shifts add up to dramatic changes. The reason behind this lunar escape: tidal forces. As Earth's rotation tugs on the moon's orbit and the moon's gravity pulls back on our oceans, energy transfers between the two bodies. This gravitational dance pushes the moon into a higher orbit while subtly slowing Earth's spin. Imagine a figure skater extending their arms to slow a spin. That's essentially what's happening to our planet. Over billions of years, days will stretch longer, tides will grow weaker, and Earth's climate could shift in unpredictable ways. Without the moon's stabilizing influence, our planet might wobble more wildly on its axis, leading to extreme weather patterns. Some scientists even speculate that life as we know it owes its existence to the moon's steady presence. Its gravitational pull helped shape Earth's early tides, possibly creating the perfect conditions for life to emerge in tidal pools. But here's the real kicker: the moon won't drift away forever. Eventually, Earth's rotation will sync up with the moon's orbit, locking both in a gravitational embrace. At that point, the same side of Earth will always face the moon, just like how we always see the same face of the moon now. Of course, by then, the sun's expansion might have already reshaped our solar system entirely. The universe operates on timescales so vast, they make human history look like the blink of an eye. Yet this gradual lunar retreat is a reminder: even the grandest celestial dances are governed by forces we're only beginning to understand. If you think diamonds are rare and precious here on Earth, wait until you hear about a planet where they might be as common as rocks. Meet 55 Cancri E, a bizarre super-Earth located about 40 light-years away in the constellation Cancer. This isn't just any rocky planet, it's a celestial jewel box with a composition so rich in carbon that scientists believe a third of its mass could be pure crystallized diamond. That's right, an entire world where the core might glitter like a cosmic diamond mine. The conditions on this planet are as extreme as its composition. Orbiting its host star at a distance 25 times closer than Mercury, is to our Sun. 55 Cancri-E's surface temperatures soar to nearly 4,000 degrees Fahrenheit, hot enough to vaporize iron and turn sand into molten glass. The day side is a scorching, molten wasteland, while the night side might be just slightly less hellish. But here's the twist: despite being dubbed the Diamond Planet, it's not some sparkling paradise. The crushing gravity and blistering heat mean any diamonds likely exist beneath the surface, trapped in a superheated, high-pressure environment where they behave more like a strange, flowing form of carbon rather than the gemstones we know. What's even more fascinating is how this world came to be. Most Earth-like planets form from silicon and oxygen-rich materials, but 55 Cancri-E's host star has an unusually high carbon-to-oxygen ratio. That chemical imbalance cooked up a planet where carbon dominates, creating the perfect conditions for diamond formation under immense pressure. Some researchers even speculate that beneath its fiery exterior, the planet's interior could host vast oceans of liquid carbon, or even exotic forms of matter we can't yet imagine. Of course, mining this diamond world is pure science fiction, not just because of the distance, but because stepping foot on it would be instant annihilation. Yet its existence challenges our understanding of planet formation, proving that the universe crafts worlds far stranger than anything we've dreamed up. Who knew that in the cosmic catalogue of planets, there'd be one that puts even the most extravagant jewelry stores to shame? Hidden behind the curtain of our Milky Way, lurking in a cosmic blind spot, lies one of the most puzzling mysteries in the universe, the Great Attractor. This invisible behemoth, situated roughly 150 million light-years away, exerts a gravitational pull so immense that entire galaxies, including our own, are being dragged toward it at speeds exceeding 1 million miles per hour. Imagine a cosmic river with thousands of galaxies caught in its current, all flowing toward some unseen destination. That's the power of this enigmatic force. What makes the Great Attractor so baffling isn't just its strength, it's the fact we can barely see it. Positioned directly behind the dense star clouds and dust of the Milky Way's galactic plane, this region is obscured by what astronomers call the zone of avoidance. It's like trying to spot a lighthouse through thick fog. Even our most advanced telescopes struggle to pierce through this interstellar veil, leaving scientists to piece together clues using radio waves and X-rays. Here's what we do know. This gravitational anomaly spans hundreds of millions of light-years and contains the mass of tens of thousands of Milky Ways. Some theorize it might be a supercluster of galaxies so densely packed together that their combined gravity creates this irresistible pull. Others speculate it could be something far more exotic, a cosmic string, a remnant from the Big Bang, or even a gateway to another universe. But the plot thickens. Recent observations reveal the Great Attractor itself is being pulled toward something even larger. The Shapley supercluster, a staggering 850 million light-years away. It's as if the universe is playing a never-ending game of tug-of-war, with galaxies as the rope. This relentless motion means that in the distant future, entire galactic neighborhoods will collide in a spectacle of cosmic proportions. While we won't be around to witness it, the Great Attractor serves as a humbling reminder: no matter how vast our galaxy seems, we're still just a speck in a much grander dance, one whose music we've only begun to hear. Venus isn't just Earth's fiery twin, it's the solar system's ultimate rebel. While nearly every planet spins counterclockwise like a spinning top, Venus defiantly rotates in the opposite direction, a phenomenon called retrograde rotation. Imagine watching a clock run backward while everything else ticks normally. That's Venus, breaking all the rules with its leisurely, upside-down spin. A single day there lasts longer than an entire year, with the sun rising in the west and setting in the east. But how did our neighbor end up so out of sync? One leading theory points to cosmic violence in the ancient past. Early in the solar system's chaotic youth, Venus may have suffered a catastrophic collision with another massive object, a hit so powerful it literally knocked the planet backward. Think of it like a billiard ball struck at just the right angle, sending it spinning the wrong way. Others argue that gravitational tug-of-war with the Sun's dense atmosphere and tidal forces could have gradually flipped Venus's rotation over billions of years. The Sun's pull, combined with the planet's thick, slow-moving atmosphere, might have acted like a brake, reversing its spin like a pendulum, slowing to a stop before swinging the other way. But here's where it gets even stranger. Venus isn't just spinning backward, it's practically standing still compared to other planets. Its axial tilt is a mere 2.6 degrees, meaning it has almost no seasons. Combine that with an atmosphere 92 times thicker than Earth's, and you've got a world where the very air acts like a heavy blanket, trapping heat and creating surface temperatures hot enough to melt lead. Some scientists propose an even wilder idea. Venus might have flipped entirely, turning upside down so that its north pole became its south pole. This could explain why its rotation appears backward without requiring a direct impact. Whatever the cause, Venus stands as a stark reminder that the universe loves throwing curveballs. Even in something as fundamental as a planet's spin, there's room for chaos, mystery, and the occasional rule breaker. The more we study Venus, the more it challenges our assumptions. Its bizarre rotation isn't just a fun fact, it's a clue to the solar system's turbulent history, written in the language of gravity, collisions, and time. And as future missions probe its toxic clouds and scorching surface, we might finally uncover the truth behind this planetary maverick. Until then, Venus remains a glittering enigma in our night sky, spinning defiantly to its own rhythm. If you thought your workday dragged on, try living on Venus, where a single day outlasts an entire year. That's not an exaggeration. While Venus zips around the Sun in just 225 Earth days, it takes a sluggish 243 Earth days to complete one full rotation on its axis. Picture this: by the time the planet finishes one leisurely spin, it's already completed a full trip around the Sun. Sunrise to sunrise, that's a staggering 117 Earth days of relentless daylight, followed by another 117 days of unbroken night. But the strangeness doesn't stop there. Venus doesn't just rotate slowly, it does so backward. Imagine the Sun creeping westward across the sky at a glacial pace, taking months to rise and months to set, all while the planet's hurricane-force winds whip its toxic clouds around at speeds up to 220 miles per hour. This creates a surreal disconnect. The upper atmosphere races around the planet every 4 Earth days, while the surface below barely budges. It's like a broken carnival ride where the top spins wildly while the base stays nearly still. Scientists call this superrotation, and it turns Venus into a planet of extremes. The same side bakes under solar radiation for months, heating the surface to 860 degrees Fahrenheit, hot enough to liquefy lead, while the night side slowly radiates that heat into the void. The sheer length of its days also means Venus lacks the magnetic field protection Earth enjoys. Without a faster spin to churn its molten core, the planet's internal dynamo remains dormant, leaving it vulnerable to the Sun's relentless particle storms. What's truly mind-bending is how this affects timekeeping. If you stood on Venus assuming you could survive its crushing pressure and acid rains, you'd need 2 separate calendars, one to track years based on its orbit, and another to count the agonizingly slow passage of days. Even the concept of a week or month would be meaningless in such an unbalanced cycle. Some researchers believe Venus's sluggish spin is tied to its thick atmosphere, a carbon dioxide blanket 90 times heavier than Earth. Like a hand dragging through water, the Sun's gravity tugs on this dense shroud, creating tidal forces that may have gradually sapped the planet's rotational energy over billions of years. Others speculate that ancient collisions or gravitational interactions with other bodies put the brakes on its spin. Either way, Venus stands as a cosmic oddity, proving that even the most basic rhythms of time can twist into something unrecognizable under the right or wrong conditions. Next to Venus, even Mercury's scorching days or Jupiter's frantic storms seem almost predictable. This world doesn't just defy expectations, it rewrites the rulebook entirely, showing us that in the universe's endless creativity, there's always room for the extraordinary. Jupiter's Great Red Spot isn't just a storm, it's a tempest so vast it could swallow our entire planet whole. For centuries, this swirling crimson maelstrom has dominated Jupiter's atmosphere, a towering vortex of gas raging at speeds over 400 miles per hour. But something unsettling is happening. This iconic storm is shrinking. Measurements show its width has halved since the late 1800s, condensing from 25,000 miles across to barely 10,000 today. That's like watching a continent-sized hurricane slowly vanish before our eyes. What's causing this cosmic fade-out? Scientists point to turbulent jet streams, rivers of gas racing around Jupiter's atmosphere that may be gradually strangling the storm. The Great Red Spot sits between two of these opposing currents, like a boulder caught between colliding tides. Over time, these winds could be eroding its edges, stealing energy and shrinking its footprint. Some researchers even suggest the storm might be starving, running low on the smaller vortices it typically consumes to sustain itself. Imagine a fire slowly burning through its last logs. That might be the fate of this ancient storm. Yet the strangest part isn't just that it's shrinking, it's changing shape. Once an oval wider than Earth, the storm now appears more circular, as if being squeezed by invisible hands. Its color has deepened too, shifting from pale pink to a rich brick red, possibly due to chemical changes as the storm churns up material from deeper in Jupiter's atmosphere. Some years it practically glows, other years it fades to a faint smudge. Could the Great Red Spot vanish entirely? Computer models suggest it might stabilize at a smaller size rather than disappear completely, but nothing's certain. If it did fade away, Jupiter's atmospheric dynamics could shift dramatically. This storm isn't just decoration, it's a planetary-scale heat engine, redistributing energy across the gas giant and influencing weather patterns thousands of miles away. Without it, Jupiter's iconic banded cloud structure might reorganize, unleashing new storms or altering wind patterns we've observed for centuries. What makes this especially haunting is the storm's age. When astronomers first spotted it in the 1600s, it may already have been raging for centuries. If it fades now, we'd be witnessing the end of a phenomenon older than modern science itself, a storm that outlasted civilizations, now potentially meeting its quiet demise as we watch. Yet Jupiter is a world of chaos and rebirth. Even if the Great Red Spot vanishes, new storms will rise. In 2017, astronomers spotted fresh crimson ovals forming nearby, perhaps the next generation of megastorms to dominate Jupiter's skies. This slow cosmic drama reminds us, even the mightiest forces in our solar system are temporary. The universe is in constant flux, writing its grandest stories not in millennia but in epochs. And as the Great Red Spot whispers its farewell, we're privileged, and perhaps a little wistful, to bear witness. Deep in the cosmic void, 12 billion light-years from Earth, floats an unimaginable treasure, a cloud of water vapor so massive it holds 140 trillion times the water in all Earth's oceans combined. This isn't just a puddle in space, it's a cosmic reservoir stretching hundreds of light-years across, surrounding a supermassive black hole at the heart of a distant quasar. The sheer scale defies logic. Enough water to fill the Pacific Ocean over 140 trillion times, existing when the universe was barely 1.6 billion years old. How could such a colossal aquatic cloud form so soon after the Big Bang? The answer lies in the chaos of the early universe. Quasars like APM 08279 plus 5255, the monster at the center of this water cloud, were cosmic powerhouses spewing energy as they devoured surrounding matter. As gas and dust swirled into the black hole's grasp, friction heated it to unimaginable temperatures, creating a radiant disk hotter than a trillion suns. This intense radiation broke apart molecules, freeing oxygen and hydrogen atoms that then recombined in cooler outer regions, forming water vapor on a scale we'd never thought possible in the universe's infancy. What's truly staggering is what this means for our cosmic timeline. Conventional wisdom suggested the early universe was too hot, too chaotic for complex molecules like water to exist in abundance. Yet here it is proof that water, the essential ingredient for life as we know it, was already widespread when galaxies were just taking shape. This discovery rewrites the story of chemical enrichment in the cosmos. Elements like oxygen shouldn't have been common so early. They're forged in stellar furnaces and scattered by supernova, processes requiring multiple generations of stars. The existence of this vapor cloud implies stars lived, died, and seeded the universe with heavy elements far faster than models predicted. Astronomers detected this aquatic leviathan not by sight, but by the telltale microwave fingerprints of water molecules' specific frequencies absorbed as the quasar's light passed through the vapor. Each dip in the spectrum revealed more about the cloud's composition, temperature, and mind-boggling density. At -63 degrees Fahrenheit, it's far colder than Earth's oceans, yet its total mass is approximately 34 billion times that of our Sun. This discovery raises profound questions. Could other primordial quasars host similar water reservoirs? Might these clouds have been the birthplaces of the first ice-rich comets, later delivering water to young planets? While we'll never drink from this distant ocean, its existence hints that the universe may have been primed for life far earlier than we dared imagine. The cosmos, it seems, has been weaving its watery magic since nearly the beginning of time itself. When a massive star collapses in a supernova explosion, it doesn't always leave behind a black hole. Sometimes the core gets crushed into something equally bizarre. A neutron star packs 1.5 times the Sun's mass into a sphere no wider than Manhattan, creating the densest objects in the known universe outside black holes. But here's what truly defies comprehension. These cosmic cinders can spin faster than a blender blade, completing hundreds of rotations every single second. The current record holder, PSRJ 1748-2446 AD, whips around at a staggering 43,000 revolutions per minute, so fast its surface moves at nearly 1/4 the speed of light. This extreme rotation starts with the conservation of angular momentum, the same physics that makes an ice skater spin faster by pulling their arms in. When a dying star collapses from the size of a solar system down to a city, its original slow rotation gets amplified to insane speeds, like a twirling figure skater suddenly shrinking to the size of a marble. The numbers are mind-bending. A newborn neutron star can spin up to 60 times per second right after formation, and some never slow down. Their magnetic fields, trillions of times stronger than Earth's, funnel intense beams of radiation that sweep across space like lighthouse beacons. We detect these as the steady pulses of pulsars. What stops these stars from tearing themselves apart? Their incomprehensible density. A single sugar cube-sized chunk of neutron star material would weigh as much as Mount Everest, held together by a state of matter that doesn't exist anywhere else. Under this crushing gravity, protons and electrons merge into neutrons, creating a quantum soup where the rules of atomic physics get rewritten. The surface is likely a crystalline crust 10 billion times stronger than steel, floating atop an ocean of superfluid neutrons that flow without friction. But the real showstopper is how these spins warp spacetime itself. At such extreme velocities, general relativity predicts the star's equator bulges outward, creating microscopic mountains no taller than a few millimeters, yet these tiny imperfections generate gravitational waves powerful enough for us to detect across the cosmos. Some neutron stars even exist in binary systems where they steal matter from a companion star, a process that can suddenly accelerate their rotation to millisecond speeds in violent events called spin-up glitches. Yet for all their ferocious energy, neutron stars are doomed to slow down. Over millennia, their powerful magnetic fields act like cosmic brakes, gradually sapping rotational energy. The oldest pulsars might tick along just once every few seconds, their beams fading as they cool into dark stellar corpses. But for now, these celestial speed demons continue their frenetic dance, proving that in the universe's menagerie of wonders, sometimes the most extreme physics plays out on scales smaller than a city block. At the heart of our solar system lies a cosmic forge so intense it defies all earthly comparisons. The Sun's core isn't just hot, it's compressed to staggering densities, with matter packed as tightly as the atoms in a bar of solid gold. Imagine taking all the weight of the Sun's outer layers, thousands of miles of searing plasma, and concentrating that crushing force into a sphere just 1% of the star's total size. This relentless gravitational pressure creates conditions where hydrogen atoms get squeezed together with such force. They overcome their natural repulsion and fuse into helium, unleashing the energy that has nourished life on Earth for billions of years. The numbers behind this process are mind-boggling. At 15 million degrees Celsius, the core's pressure reaches 250 billion times what we experience at sea level, enough to compress hydrogen gas into a state 15 times denser than lead. In this unimaginable environment, particles move with such frenetic energy that when they collide, quantum tunneling allows their nuclei to merge despite electromagnetic forces trying to push them apart. Each second, 600 million tons of hydrogen undergo this alchemical transformation, with about 4 million tons converted directly into pure energy according to Einstein's famous equation. That's the equivalent of detonating 90 billion 1 megaton nuclear bombs every single second. What's truly remarkable is how this process balances on a knife's edge. The outward pressure from fusion reactions perfectly counteracts gravity's inward crush, maintaining stellar equilibrium for billions of years. If fusion slowed, the Sun would contract and heat up until reactions reignited. If it accelerated, the star would expand and cool. This self-regulating mechanism is why our Sun burns so steadily compared to the violent flares of younger, less stable stars, a cosmic thermostat fine-tuned by the laws of physics. This relentless fusion factory doesn't just produce light, it generates the very elements that make our existence possible. Every carbon atom in your body, every oxygen molecule you breathe, was forged in stellar cores like this one, then scattered across space by ancient supernova. The gold in your jewelry that required even more extreme conditions, the cataclysmic collision of neutron stars. Yet it all traces back to these crushing densities at a star's heart, where ordinary matter transforms into something extraordinary under pressures we can scarcely imagine. While we'll never directly sample the Sun's core, its influence reaches us across 93 million miles of space, warming our planet and driving Earth's climate systems. Even more astonishing, the sunlight touching your skin right now began its journey tens of thousands of years ago, spending most of that time as a wayward photon bouncing between atoms in the Sun's dense interior before finally breaking free. That golden heart doesn't just power our present, it connects us to the deep time of the cosmos itself. HD 189733b isn't your typical rainy world. It's a nightmare vacation spot where the skies rain molten glass sideways at thousands of miles per hour. Located 63 light-years away in the constellation Vulpecula, this cobalt-blue exoplanet looks deceptively serene from afar, like a tranquil Earth twin. But zoom in, and you'll find a hellscape of unimaginable fury. Winds here scream across the planet at 5,400 miles per hour, 7 times the speed of sound, and nearly twice as fast as the most violent tornadoes on Earth. These aren't gentle breezes carrying raindrops, They're supersonic hurricanes hurling microscopic shards of silicate glass like celestial shotgun blasts. The rain isn't water, it's vaporized rock. Here's how this glass storm happens. Daytime temperatures on HD 189733b reach a blistering 1,700 degrees Fahrenheit, hot enough to vaporize silicate minerals in its atmosphere. As these particles get whipped to the planet's cooler night side by those insane winds, they condense into tiny glass droplets, but there's no peaceful fall to the ground. The relentless gales sweep this molten glass sideways in horizontal tempests that would shred any spacecraft to confetti in seconds. The planet's eerie blue hue, initially mistaken for the reflection of an ocean, actually comes from this glass haze scattering starlight, similar to how Earth's atmosphere scatters sunlight to create our blue sky, but cranked to a lethal extreme. Locked in a tight orbit just 3 million miles from its host star, 30 times closer than Earth is to the Sun, the planet's day side is perpetually scorched while its night side simmers in eternal twilight. What makes this world especially bizarre is its synchronization. Like our moon to Earth, HD 189733b is tidally locked. One side always faces its star in broiling daylight while the other languishes in darkness. This creates a perpetual temperature gradient that fuels those insane winds, as atmosphere rushes from the hot side to the cold in a never-ending attempt to balance the energy. Scientists first uncovered these horrors by observing how the planet's atmosphere filters starlight during transits. Spectral analysis revealed the telltale signature of silicate particles, the building blocks of glass, while Doppler measurements detected wind speeds that dwarf anything in our solar system. There's even evidence of hydrogen atoms being torn from the atmosphere and blown into a comet-like tail by the star's radiation. This isn't just a curiosity, it's a window into how extreme physics shapes alien worlds. Planets like HD 189733b challenge our assumptions about atmospheric dynamics, showing us environments where familiar processes twist into unrecognizable forms. If rain on Earth nurtures life, here it's a hallmark of cosmic violence, a reminder that the universe isn't just stranger than we imagine, but often far more brutal. If you could take a deep breath in the heart of the Milky Way, it might smell like a cosmic cocktail bar, rich with the sugary sweetness of raspberries and the sharp, warm bite of rum. This isn't science fiction, it's chemistry on a galactic scale. Astronomers have discovered vast clouds of ethyl formate floating in interstellar space, the same organic compound that gives raspberries their signature aroma and contributes to rum's distinctive scent. These molecular clouds, sprawling light years across, are essentially giant distilleries brewing the essence of desserts and spirits in the vacuum of space. So how do we smell something billions of miles away? The answer lies in the universe's hidden fingerprint spectroscopy. When starlight passes through these cosmic gas clouds, molecules like ethyl formate absorb specific wavelengths of light, leaving dark lines in the spectrum like a barcode. Each molecule has its own unique pattern, allowing astronomers to identify them with astonishing precision. It's like catching whiffs of a perfume based on the light shining through its bottle. The discovery came from studying Sagittarius B2, a massive molecular cloud near the center of our galaxy, where telescopes detected the chemical signatures of not just ethyl formate but dozens of other complex organic molecules, from ethanol, the alcohol in drinks, to glycolaldehyde, a simple sugar. What makes this especially mind-bending is how these molecules form in the first place. Space might seem empty, but it's actually a sprawling chemical laboratory. Dust grains act as tiny scaffolding, allowing atoms to meet and bond in the frigid vacuum. When ultraviolet light or cosmic rays hit these grains, they trigger reactions that build increasingly complex molecules, like a slow-motion baking process where the ingredients are scattered across light years. Over millions of years, these clouds become reservoirs of life's building blocks, proving the universe has a sweet tooth long before planets or life emerged. But here's the twist: while the Milky Way might smell delicious, you wouldn't actually want to inhale it. These molecular clouds are also laced with toxic compounds like hydrogen sulfide, which smells like rotten eggs and deadly cyanide. The raspberry rum aroma is just one note in a far more dangerous symphony. Yet this discovery reshapes how we think about the cosmos. If the ingredients for flavors we recognize, and even the precursors to life's chemistry, are floating between the stars, it hints that the universe might be primed for complexity everywhere we look. Next time you taste a raspberry or sip a fine rum, remember, somewhere in the depths of space, the same molecules are swirling in an endless dance, waiting to become part of future worlds, or perhaps future cocktails. The universe isn't just vast and mysterious, it's also strangely, wonderfully familiar. In the vast emptiness of space, there's one thing you'd never hear: sound itself. Unlike Earth's bustling soundscape, where waves travel through air, water, or solid ground, the cosmic void is utterly silent. Sound needs molecules to vibrate and carry it forward, but space is nearly a perfect vacuum, so sparse that particles are miles apart, leaving nothing to transmit those vibrations. If you were floating near a supernova explosion, you wouldn't hear a thing, even as the shockwave ripped through space with enough energy to vaporize planets. This eerie silence defies almost every Hollywood depiction of space battles, where lasers whoosh and starships roar. In reality, those dramatic explosions would play out in chilling quiet, like a nightmare on mute. Astronauts experience this firsthand. During spacewalks, they've described the surreal contrast of watching tools clatter against the International Space Station's hull without a single clink reaching their ears. The only sounds come through vibrations in their suits or headsets, voices from mission control, the hum of life support systems, or their own breath echoing inside their helmets. So how do astronauts communicate? Radio waves. Unlike sound, these electromagnetic pulses don't need a medium to travel. They zip through the void at the speed of light, carrying voices across thousands of miles as clearly as a phone call. But even this lifeline has limits. When spacecraft pass behind the moon or planets, signals can drop out completely, leaving astronauts isolated in the most profound silence imaginable. The implications of this silence stretch beyond human experience. Entire cosmic events colliding galaxies, swirling nebulae, dying stars unfold in perfect quiet, their dramas visible only through telescopes. Some scientists speculate that if space weren't silent, the combined noise of the universe would be deafening, a cacophony of countless explosions and collisions. Instead, we get haunting stillness, a reminder that the universe communicates not through sound, but through light, gravity, and the invisible forces shaping the cosmos. Yet there's a strange beauty to this silence. It means every creak of a spaceship, every spoken word between astronauts becomes precious, a tiny bubble of sound in an ocean of quiet. And when those sounds fade, you're left with something far more profound, the overwhelming realization that in space, no one can hear you gasp. Beyond the known planets, lurking in the solar system's frozen outskirts, there might be a hidden giant planet 9. This isn't just speculation, it's a hypothesis backed by strange gravitational fingerprints scattered across the Kuiper belt, the ring of icy debris beyond Neptune. Since 2014, astronomers have noticed clusters of these distant objects moving as if tugged by something massive, something with 10 times Earth's mass, orbiting 20 times farther from the Sun than Neptune. The math suggests an unseen planet is herding these icy bodies into odd, tilted orbits like a cosmic sheepdog. What makes Planet 9 so compelling isn't just the orbital oddities, it's the sheer scale of its proposed path. If real, this world would follow a wildly elongated orbit, swinging between 300 and 700 astronomical units from the Sun. That's so distant, sunlight would take days to reach it, and a single orbit might take up to 20,000 Earth years. Spotting it would be like finding a charcoal briquette in the blackness of space, illuminated only by the faintest glow of starlight. Even our best telescopes, like the Subaru Observatory in Hawaii, have only scanned a fraction of the sky where it might hide. Theories about this phantom planet's origins are just as fascinating. Some suggest it formed closer to the Sun before getting flung outward by gravitational encounters with Jupiter or Saturn, a cosmic game of planetary pinball. Others propose it might be a rogue exoplanet, captured by the Sun's gravity after being ejected from another star system entirely. Its composition could range from a rocky super-Earth to a smaller version of Uranus, wrapped in a thick hydrogen-helium cloak. Yet the lack of direct detection has skeptics questioning whether Planet 9 exists at all. Alternative explanations, like the collective gravity of many smaller Kuiper belt objects or even subtle distortions from dark matter, could theoretically explain the anomalies too. But until we rule out a massive planet, the hunt continues, with researchers poring over old telescope data and running simulations to narrow down its possible hiding places. If found, Planet 9 would rewrite solar system history. Its gravitational influence might explain other mysteries, like why the solar system's plane tilts slightly compared to the Sun's equator, or why some distant objects orbit backward. This hypothetical world reminds us that even in our own cosmic backyard, there are still shadows left to explore, and perhaps giants waiting to be discovered. You'd expect the coldest place in the universe to be in the depths of interstellar space, far from any star's warmth, but nature has a way of surprising us. The Boomerang Nebula, located 5,000 light-years away in the constellation Centaurus, holds the cosmic record for natural cold, with temperatures plunging to -458 degrees Fahrenheit. That's just 1 degree above absolute zero, the theoretical temperature where all molecular motion stops. This eerie, bow-tie-shaped cloud of gas is colder than even the background radiation left over from the Big Bang, which hovers around -454 degrees. But here's the twist: humanity has outdone the cosmos in the chill department. In a lab at MIT, scientists used lasers and magnetic fields to cool sodium-potassium molecules to a staggering -459.67 degrees 250 nanokelvin, making it the coldest spot ever recorded, right here on Earth. Creating such extreme cold isn't as simple as cranking up a cosmic air conditioner. To reach these record lows, physicists employ a technique called laser cooling, where carefully tuned beams of light act like microscopic brakes on atoms. Imagine shining a spotlight on a speeding car, except the light particles don't just illuminate the car, they physically slow it down by transferring momentum. By bombarding atoms with lasers from multiple directions, researchers can sap their energy, cooling them to within a whisper of absolute zero, but that's only half the battle. To push temperatures even lower, scientists use evaporative cooling in magnetic traps, letting the most energetic atoms escape like steam from a boiling pot, while the remaining sluggish atoms form an ultra-cold cloud. What's truly bizarre is how matter behaves at these temperatures. Atoms near absolute zero merge into a single quantum state called a Bose-Einstein condensate, where they lose their individual identities and act as one superatom. Light slows to a crawl, and fluids defy gravity, creeping up container walls in a phenomenon called superfluidity. These experiments aren't just about breaking records, they're testing the boundaries of quantum mechanics, potentially paving the way for unhackable quantum computers or materials with zero energy loss. Yet the Boomerang Nebula's natural deep freeze remains a marvel in its own right. This cosmic icebox gets its chill from a dying star at its core, hurtling gas outward at 370,000 miles per hour, so fast that the expanding gas cools more efficiently than any refrigerator. It's a reminder that while we've mastered extreme cold in labs, the universe still holds mysteries we can't yet replicate. From the depths of space to basement laboratories, the quest to push temperature limits reveals just how strange and interconnected the physics of the very large and the very small can be. A teaspoon of sugar might weigh a few grams on Earth, But if you scooped that same teaspoon from the surface of a neutron star, you'd be holding something with the mass of 1 billion tons, equivalent to stacking 500,000 pickup trucks into an impossibly dense cube. That's the mind-warping reality of neutron stars, where matter gets squeezed so tightly, the very structure of atoms collapses. Imagine taking Mount Everest, crushing it down to the size of a sugar cube, and still having enough leftover weight to flatten a city. That's the level of compression we're talking about. How does matter become this dense? When a massive star exhausts its fuel and explodes as a supernova, its core collapses under gravity's relentless pull. Electrons and protons get crushed together so violently, they merge into neutrons, eliminating the empty space inside atoms. The result is a city-sized sphere where a single cubic centimeter packs as much mass as all the cars, buildings, and people on Earth combined. Under this pressure, neutrons themselves break down into a quantum soup of quarks and gluons particles that normally only exist fleetingly in particle accelerators. To grasp just how extreme this is, picture Earth's entire population crammed into a single raindrop. That's the scale of density we're dealing with. If you dropped a fragment of neutron star material onto our planet, it wouldn't just sink, it would slice through the crust like a bullet through tissue paper, oscillating through the molten core until friction finally brought it to rest at the center. Even a speck the size of a grain of sand would weigh millions of pounds, warping space-time around it like a miniature black hole. What's truly bizarre is how this density affects time itself. The gravitational pull near a neutron star is so intense, clocks would tick noticeably slower there compared to Earth. If you could stand on its surface, ignoring the fact that you'd be instantly vaporized, you'd age slower than someone back home, a real-life twist on interstellar time dilation. Yet for all their crushing weight, neutron stars aren't just inert cosmic boulders. Many spin hundreds of times per second, some emitting beams of radiation that sweep across the universe like lighthouse beacons. These are the pulsars astronomers detect from thousands of light-years away. Others, called magnetars, generate magnetic fields a quadrillion times stronger than Earth's, capable of ripping apart atoms from halfway across the solar system. This extreme physics isn't just theoretical. In 2017, the collision of two neutron stars sent gravitational waves rippling through the cosmos, proving these objects forge heavy elements like gold and platinum in their violent mergers. That means the ring on your finger might contain stardust from one of these cataclysmic crashes. The universe has a way of packing unimaginable scale into tiny packages, and nothing proves that quite like a neutron star where a teaspoon holds the weight of worlds. The universe isn't just vast and dark, it's also surprisingly lukewarm. No matter where you float in space, you'll encounter a faint but unmistakable warmth radiating from every direction. The cosmic microwave background, a relic of the Big Bang that permeates the entire cosmos like an echo that never fades. This afterglow, discovered accidentally in 1965, clocks in at a crisp 2.7 Kelvin, just a hair above absolute zero. While that might sound icy, it's actually the universe's way of holding onto the heat of its birth 13.8 billion years later. This omnipresent glow isn't just random noise, it's the oldest light in existence, photons that have been traveling since the universe was a seething plasma soup, 380,000 years after the Big Bang. Back then, space was so dense and hot that light couldn't travel far without crashing into particles, making the cosmos opaque like a thick fog. But as the universe expanded and cooled, electrons and protons finally combined into hydrogen atoms, clearing the fog and unleashing those trapped photons in a flash. Stretched by eons of cosmic expansion, that primordial light shifted from visible wavelengths to microwaves, creating the faint hum we detect today. The discovery of this background radiation was a watershed moment for cosmology. When Arno Penzias and Robert Wilson first picked up this persistent static with their Bell Labs radio antenna, they initially blamed pigeon droppings on their equipment. But after scrubbing the antenna and still detecting the signal, they realized they'd stumbled onto something monumental, direct evidence of the universe's fiery beginning. This finding demolished competing theories like the steady-state model and cemented the Big Bang as the leading explanation for our cosmic origins. What's even more astonishing is how uniform this temperature appears. No matter which way we point our telescopes, the variations are minuscule, differing by less than 1/1000th of a degree. These tiny fluctuations, mapped in exquisite detail by satellites like COBE and Planck, are the blueprints for the cosmic structures we see today. The slightly denser patches in that early glow seeded the gravitational collapse that formed galaxies and galaxy clusters, meaning the universe's large-scale architecture owes its existence to these microscopic wrinkles in spacetime. But here's the cosmic irony: this thermal fingerprint is growing colder. As the universe continues expanding, the wavelength of this radiation stretches further, gradually redshifting toward lower energies. Billions of years from now, future civilizations might detect it as feeble radio waves, and eventually it could fade beyond recognition altogether. Until then, it remains the most compelling snapshot of our universe's infancy, a baby picture etched in microwaves, proving that even in the deepest voids of space, the Big Bang's warmth still lingers. If you think Earth's golden sunsets are breathtaking, wait until you see the skies of Mars, where the sun dips below the horizon in a surreal wash of blue. This otherworldly spectacle isn't just artistic license from sci-fi movies. It's science in action, captured firsthand by rovers like Curiosity and Perseverance. While our sunsets paint the sky in fiery reds and oranges, Mars flips the script, bathing its dusty plains in cool, ethereal hues that look more like an Arctic twilight than a desert dusk. The secret lies in the Martian atmosphere's unique chemistry. Earth's sky turns red at sunset because our thick, nitrogen-rich air scatters shorter, blue wavelengths of sunlight throughout the day, leaving the longer red and orange wavelengths to dominate when the sun is low. But Mars's wispy atmosphere, just 1% as dense as Earth's, is choked with fine iron-rich dust particles. These tiny grains, smaller than the wavelengths of light itself, preferentially scatter the red light away, allowing the cooler blue tones to pierce through. It's the opposite of what happens on Earth, like swapping a warm oil painting for a watercolor in shades of cobalt and sapphire. NASA rovers have gifted us front-row seats to this phenomenon. Time-lapse images from Curiosity show the sun shrinking to a mere third of its earthly size as it sets, its light diffusing into a hazy blue glow that lingers long after the star vanishes. Without the intense glare of our thick atmosphere, Martian sunsets reveal subtle layers of color, with the sky near the sun transitioning from buttery yellow to pale blue, while the horizon opposite glows a faint pink, a lingering kiss of the scattered red light. What makes this even more fascinating is how variable these sunsets can be. During global dust storms, when the entire planet is blanketed in airborne silt, the blue effect intensifies as even more red light gets filtered out. On clearer days, the sunset might appear more muted, with hints of purple or gray. It's a dynamic show dictated by the whims of Martian weather, proving that even on a world with barely any air, the sky can put on a performance to rival Earth's most vivid sunsets. This isn't just a pretty sight, it's a clue to Mars's environmental history. The prevalence of fine dust suggests eons of erosion, where once flowing water and relentless winds ground rocks into the tiny particles that now dance in the thin air. Every sunset, then, is a silent testament to the planet's dramatic past, written in hues no human eye had witnessed until our robotic explorers beamed back the evidence. So next time you watch the sun sink below Earth's horizon, spare a thought for Mars, where twilight comes in shades of another world, a quiet reminder that even the most familiar phenomena can twist into something extraordinary under alien skies. In the vast cosmic web where galaxies cluster like glittering cities, there exists a place so empty it defies comprehension, the Boötes void. Picture a spherical region of space 330 million light-years wide, large enough to swallow thousands of Milky Ways, yet containing fewer than 60 galaxies. If our galaxy were placed here, astronomers in neighboring voids might scan the darkness for billions of years before spotting another island of stars. This isn't just a quiet corner of the universe, it's a cosmic desert so barren. Scientists initially dismissed its existence as an instrument error. So how does a void this colossal form? One leading theory points to the aftermath of cosmic inflation, the rapid expansion of the universe moments after the Big Bang. Tiny quantum fluctuations in that primordial burst may have stretched into vast underdense regions, leaving behind bubbles of near-nothingness as the cosmos grew. Another possibility involves dark energy's accelerating push, which could have amplified smaller voids over billions of years, merging them into this staggering emptiness. Some even speculate about more exotic explanations, like the void being a scar from a collision with another universe in the multiverse, leaving behind a patch of sterile space-time. But the most tantalizing and controversial hypothesis involves advanced civilizations. The Fermi paradox asks why we haven't detected alien life despite the universe's vastness. One answer, maybe extraterrestrial societies expand so exponentially that they eventually harness the energy of entire galaxies, leaving behind hollowed-out regions like the Boötes void as they migrate toward richer cosmic structures. It's a wild idea, but the void's extreme underdensity makes it a provocative candidate for what theorists call a Type 3 civilization's footprint. Despite its eerie emptiness, the Boötes void isn't completely lifeless. The few galaxies trapped inside are peculiar, isolated, field galaxies that may have been drifting alone since the universe's youth. These loners offer unique insights into how galaxies evolve without neighbors to collide with or cannibalize. Some even appear unusually rich in hydrogen, as if frozen in time from an earlier cosmic era. What makes this void truly humbling is its scale. If you could teleport to its center, the night sky would appear almost pitch black, with just a handful of faint smudges breaking the darkness. No constellations, no Milky Way band, just an endless void staring back. It's a visceral reminder that the universe isn't just full of wonders, it's also studded with absences profound enough to make even the brightest galactic clusters feel insignificant. Whether a relic of cosmic infancy, a byproduct of dark energy, or something even stranger, the Boötes void challenges our understanding of how structure emerges in the universe. And as telescopes probe deeper into its darkness, we might find that the emptiest places hold the most surprising secrets. Saturn's rings aren't just breathtaking, they're vanishing before our eyes. That iconic celestial halo, wide enough to fit 6 Earths side by side, is actually raining down on the planet in a slow-motion cosmic waterfall. NASA Cassini spacecraft discovered this phenomenon during its final orbits, detecting enough icy ring material plunging into Saturn's atmosphere every half hour to fill an Olympic-sized swimming pool. At this rate, astronomers estimate the entire ring system could disappear within 100 million years, a blink of an eye in cosmic terms. What's causing this celestial demolition? Saturn's immense gravity acts like a celestial vacuum cleaner, pulling in the ring particles through a process called ring rain. The planet's magnetic field funnels water ice from the rings along invisible lines of force, creating dazzling auroras where these particles collide with the upper atmosphere. But there's more to the story than gravity alone. Ultraviolet light from the sun and micrometeoroid impacts electrically charge the ice particles, making them vulnerable to Saturn's magnetic pull. It's like cosmic dust being drawn to a planetary-scale electrostatic balloon. The rings themselves are surprisingly fragile, most no thicker than a 2-story building despite spanning over 270,000 miles. Made of billions of chunks ranging from dust grains to house-sized boulders, they orbit at different speeds depending on their distance from Saturn. This creates those distinctive gaps and waves seen through telescopes. But this delicate dance is temporary. Based on their composition and brightness, scientists believe the rings are relatively young, perhaps only 100 to 300 million years old, meaning dinosaurs might have walked Earth when they first formed from the shattered remains of a moon or comet. What's truly remarkable is how fast they're deteriorating. Saturn's inner rings are disappearing particularly quickly, with the D ring, the one closest to the planet, already looking patchy and faint. At the current loss rate, the entire ring system could dwindle to a mere shadow of itself within tens of millions of years. Future civilizations might gaze at Saturn through telescopes and see only a naked gas giant, its spectacular rings reduced to thin, dark bands of leftover debris. This discovery changes how we understand ring systems throughout the universe. If Saturn's rings are this ephemeral, other ringed planets we've discovered orbiting distant stars might represent brief, spectacular phases in planetary evolution rather than permanent features. It also makes our current era special. We're living during the golden age of Saturn's rings, when they're at their most visible and photogenic. The next time you see an image of Saturn's glittering rings, remember, you're witnessing a cosmic masterpiece that won't last forever. The moon may look like a silent, lifeless world, but beneath its cratered surface, it's actually trembling with seismic activity. These lunar quakes, or moonquakes, were first discovered by Apollo astronauts who left seismometers on the surface between 1969 and 1972. The instruments recorded thousands of quakes over 8 years, some gentle tremors, others shaking with enough force to register up to 5.5 on the Richter scale. That's strong enough to crack concrete walls or topple unsecured equipment, a serious concern for anyone planning to build permanent lunar bases. What causes these quakes on a world without tectonic plates? Unlike Earth, where earthquakes stem from shifting crustal plates, the moon has a different seismic menu. The most powerful moonquakes originate deep in the mantle, triggered by tidal forces as Earth's gravity stretches and squeezes the moon's interior like a cosmic stress ball. These deep quakes can last up to 10 minutes, far longer than the brief, sharp jolts we experience on Earth because the moon's dry, rigid structure allows vibrations to echo endlessly. Imagine ringing a bell in a soundproof room versus a cathedral. The moon is the cathedral, with seismic waves reverberating through its brittle crust without dampening. But tidal forces aren't the only culprit. Meteor impacts send shockwaves rippling through the lunar surface, creating shallow, high-frequency quakes. The moon lacks an atmosphere to burn up incoming space rocks, leaving it vulnerable to constant bombardment. Even the extreme temperature swings between lunar day and night, ranging from 250 degrees Fahrenheit to negative 280, cause the crust to expand and contract, generating thermal moonquakes near the surface. Apollo seismometers picked up these regular, clock-like tremors every morning as sunlight warmed the frozen ground. For future lunar settlers, these quakes aren't just scientific curiosities, they're logistical nightmares. The moon's lack of erosion means seismic waves travel farther and hit harder than on Earth. A magnitude 5 quake here might rattle dishes, but on the moon it could destabilize entire habitats. Dust kicked up by tremors would cling to everything due to static electricity, clogging machinery and life support systems. Engineers are already designing shock-absorbing foundations and flexible structures to withstand these tremors, taking cues from earthquake-resistant buildings on Earth. The silver lining, moonquakes also offer a window into the moon's hidden interior. By analyzing how seismic waves travel, scientists have mapped its layers, discovering a partially molten core and a fractured outer shell. Some speculate these cracks might provide access to underground lava tubes, natural shelters from radiation and micrometeorites. In a twist of cosmic irony, the very forces that threaten lunar bases might also point the way to their safest locations. One lingering mystery is why some moonquakes cluster in specific regions like the South Pole, a prime target for upcoming crewed missions. Are these hotspots hinting at subsurface magma left over from the moon's volcanic past, or are they stress points where the crust is still adjusting after billions of years of cooling? Each tremor carries clues, making the moon not just a destination for explorers, but an ongoing planetary science experiment. The next time you gaze at its serene face, remember beneath that calm exterior lies a world that never stops shaking. Deep in the constellation Libra, hidden among countless younger stars, lies a cosmic conundrum HD 140283, nicknamed the Methuselah Star. This ancient beacon, shining just 190 light-years from Earth, holds a secret that upends our understanding of cosmic timelines. Based on detailed measurements of its composition and brightness, astronomers calculate its age at a staggering 14.5 billion years. There's just one problem. The universe itself is only 13.8 billion years old. That means this star appears to predate the very fabric of space-time it inhabits, like finding a fossil older than the planet it rests upon. How can a star exist before the universe began? The answer lies in the delicate art of stellar archaeology. Determining a star's age isn't as simple as checking a cosmic birth certificate. It requires analyzing the subtle fingerprints of its light. Astronomers study the Methuselah star's spectrum to measure its abundance of heavy elements and compare them to models of stellar evolution. Its extremely low metal content, just 1% of the Sun's, suggests it formed from nearly pristine gas, untouched by generations of supernova, a hallmark of the universe's first stellar population. Yet the paradox persists, and scientists have proposed several ways to resolve it. The most compelling explanation involves tweaking our measurements of cosmic expansion. The star's age estimate depends partly on its distance, which was recalculated in 2014 using Hubble's precise parallax measurements. These new figures shaved off nearly a billion years from earlier estimates, but uncertainties remain. Some researchers argue the star might be closer than we think, making it intrinsically dimmer and therefore younger than current models suggest. Others point to quirks in stellar physics, suggesting the Methuselah star might have formed with an unusually high oxygen content, skewing age calculations. The most mind-bending possibility involves our fundamental understanding of the early universe. Could the Big Bang not be the true beginning, but rather a phase transition from some earlier state? If so, the Methuselah star might carry chemical signatures from a cosmic epoch we've yet to comprehend, like a message in a bottle from beyond spacetime's horizon. While most cosmologists dismiss this as speculative, the star's very existence forces us to refine our models, proving that even our best theories are works in progress. What makes this discovery truly humbling is how ordinary the Methuselah star looks. Through amateur telescopes, it appears as just another faint dot of light, indistinguishable from its younger neighbors. Yet within its unassuming glow lies a challenge to everything we thought we knew about time's arrow. Whether a measurement error, a cosmic outlier, or a clue to deeper physics, this ancient sentinel reminds us the universe always keeps a few secrets in reserve. While most planets spin like tops as they orbit the Sun, Uranus rolls around our star like a cosmic bowling ball, tipped over at a jaw-dropping 98-degree angle. This extreme tilt means its poles take turns pointing directly at the Sun during its 84-year orbit, creating seasons more bizarre than anything in our solar system. Picture a world where winter means 42 straight years of darkness, where the Sun circles the horizon like a wary predator before finally plunging the hemisphere into an icy twilight that lasts generations. The reason behind this sideways spin remains one of the solar system's greatest whodunits. The leading theory, a cataclysmic collision with an Earth-sized protoplanet in Uranus's youth, a hit so violent it essentially knocked the planet on its side. Computer simulations show such an impact wouldn't just tilt Uranus. It could also explain why the planet's interior radiates surprisingly little heat compared to other gas giants. The collision might have blasted away much of its primordial warmth, leaving behind an oddly chilly world with an off-kilter rotation. But there's a twist. Some scientists argue a series of smaller impacts could have produced the same tilt, like repeated shoves to a spinning top. Others propose gravitational interactions with Saturn or Jupiter during the solar system's chaotic early days might have gradually torqued Uranus into its current position. Whatever the cause, the result is a planet where the rules of seasons get thrown out the window. During solstices, one pole bakes under constant sunlight while the other freezes in eternal night, despite both regions being roughly the same temperature due to the planet's sluggish heat distribution. Come equinox, Uranus's equator faces the sun, creating a fleeting period of normal days and nights across its cloudy atmosphere. But even these are strange. The planet's rapid 17-hour rotation combined with its tilt generates lopsided weather patterns, including diamond rain and swirling polar vortices wider than Earth. The most striking consequence of this tilt, Uranus's magnetic field, is a mess. Unlike Earth's relatively aligned magnetic poles, Uranus's field axis is tilted 60 degrees from its already sideways spin axis, creating a corkscrewing magnetosphere that flips on and off like a broken compass as the planet rotates. This chaotic field might explain why Uranus's atmosphere leaks gas into space at rates far higher than Neptune's, a literal sideways planet with a magnetism to match. Future missions could finally solve the mystery of how Uranus got knocked over, but for now, it remains a glaring outlier in our solar system's family portrait. Its extreme tilt isn't just a curiosity, it's a frozen record of the violence that shaped all the planets, reminding us that even in the seeming order of our cosmic neighborhood, chaos leaves its mark. The next time you picture Uranus, imagine it rolling through space like a wayward barrel, carrying the scars of an ancient impact that forever changed its place in the sun. Ever dreamed of growing taller overnight? Astronauts get to experience this surreal phenomenon temporarily thanks to the magic of microgravity. Without Earth's constant downward pull, their spines stretch like accordions, adding up to 2 inches in height during long missions. It's not an optical illusion. It's a startling anatomical shift that turns the International Space Station into an accidental height enhancement lab. The science behind this cosmic growth spurt hinges on our spine's natural design. On Earth, gravity compresses the vertebral column, squishing the cartilage discs between each bone like stacked marshmallows. But in weightlessness, these discs no longer crushed by body weight expand, creating space between vertebrae. Imagine a coiled spring suddenly released, gently lengthening as tension vanishes. That's essentially what happens to an astronaut's backbone, millimeter by millimeter, over weeks in orbit. This extra height comes at a price. Stretched spines often lead to excruciating back pain as muscles and ligaments strain to adapt. Some astronauts report persistent discomfort, like wearing a body that no longer fits properly. Even more troubling, the return to Earth's gravity reverses the process abruptly, slamming expanded discs back into compression. That's why homecoming crews are carefully monitored. Sudden spinal shrinkage can pinch nerves or trigger herniated discs. Mission medics jokingly call it cosmic shrinking syndrome, but the risks are very real. The effects don't stop at the spine. Microgravity redistributes bodily fluids too, causing faces to puff up and legs to slim down as blood and water migrate toward the head. Combined with spinal elongation, this creates a bizarre pencil legs, swollen head, silhouette astronaut's nickname, Space Bird. While most fluid shifts normalize within hours of landing, spine recovery takes weeks. Some astronauts never fully return to their pre-flight height, retaining about an inch of permanent stretch, a subtle souvenir from living among the stars. Future missions to Mars pose new worries. 6 months to a year in microgravity could exaggerate these changes, potentially leaving explorers taller but weaker upon arrival. Scientists are testing countermeasures, from specialized exercise suits that simulate gravity to vibrating plates that stimulate bone growth. but for now, space's stretching effect remains an unavoidable side effect of venturing beyond Earth. So while astronauts might enjoy a temporary boost in stature, they're paying for it in ways that remind us gravity isn't just a force, it's the invisible glue holding our bodies together. The sun doesn't just shine, it sings. Beneath its churning surface, our star pulses with deep, resonant vibrations, a symphony of pressure waves that scientists have transformed into an eerie, otherworldly hum. Using data from satellites like NASA's Solar and Heliospheric Observatory, researchers converted these ultra-low-frequency oscillations into sound waves audible to human ears, revealing a celestial melody unlike anything on Earth. The result, a haunting, bass-heavy drone like the lowest notes of a pipe organ stretched across time, vibrating at frequencies that would make your chest rumble if you could stand close enough to hear it. These solar sounds aren't random noise, they're the heartbeat of a star. Convection currents in the sun's outer layers generate pressure waves that ricochet through its interior, a process called heliosysmology. Imagine billions of tiny earthquakes rippling through the sun's plasma, some taking hours to complete a single oscillation. These vibrations create standing waves that reveal the star's hidden structure, much like how seismic waves map Earth's interior. By studying them, astronomers can see deep into the sun's core, tracking rotation rates and even predicting solar flares. What makes these sounds so unsettling is their scale. The original frequencies are far too low for human ears, about 3 MHz or one vibration every 5 minutes. To make them audible, scientists sped up the data by 42,000 times, shifting it into our hearing range. The deeper the tone, the closer to the sun's core the wave originated. Some notes correspond to plasma loops arcing through the corona, while others trace the dance of superheated gas near the radiative zone. This sonic window into stellar physics isn't just for scientific curiosity, it's reshaping how we understand stars. The sun's vibrations follow patterns similar to musical chords, with overtones and harmonics that reflect its composition and age. Younger stars sing at higher pitches, while older, swollen stars produce deeper, slower rumbles. If stars could be heard across the void of space, the Milky Way would hum with a chorus of these cosmic frequencies, each one a fingerprint of its life cycle. Yet there's a chilling edge to this discovery. The sun's song isn't static, it changes with solar activity. During violent flares or coronal mass ejections, the tones warp into dissonant shrieks as magnetic upheavals disrupt the star's rhythm. It's a reminder that our seemingly steady sun is a dynamic, turbulent beast, its melody a real-time soundtrack to the forces that shape our solar system. For all its beauty, this soundscape is also a warning. The same vibrations that help us peer inside the sun could one day alert us to catastrophic solar storms, giving astronauts and power grids precious hours to prepare. So while we'll never stand on the sun's surface to hear its true voice, these translated echoes offer something just as valuable, a deeper connection to the star that gives us life, written in frequencies only science can translate. Deep in the heart of the Milky Way, about 26,000 light-years from Earth, floats a cosmic distillery of staggering proportions, the Sagittarius B2 molecular cloud. This gigantic region of gas and dust, spanning over 150 light-years across, contains something that would make any terrestrial bartender's jaw drop. Billions upon billions of liters of ethyl alcohol, the very same compound that gives beer and whiskey their intoxicating kick. If you could somehow bottle this interstellar booze, it would fill enough shot glasses to keep every human on Earth happily buzzed for trillions of years. But before you picture alien civilizations hosting the galaxy's wildest happy hour, there's a catch. This alcohol isn't floating around in liquid form. Instead, it exists as vapor, mixed with a cocktail of other complex organic molecules like formaldehyde, acetic acid, and even sugar-like compounds called glycolaldehyde. These ingredients don't exist for our amusement. They're actually the building blocks of something far more profound: stars and potentially life itself. What makes Sagittarius B2 so special is how these molecules form in the harsh vacuum of space. The cloud's dense cores, shielded from starlight by layers of dust, act as cosmic chemistry labs. Here, atoms and simple molecules stick to the surface of icy dust grains, where they collide and react over millennia, eventually forming more complex compounds like ethanol. When new stars ignite nearby, their radiation warms these ices, releasing the molecules into space as gas, creating the sprawling alcoholic haze we detect with radio telescopes. The real magic happens when these alcohol-rich clouds collapse under gravity, forming new stellar nurseries. Complex molecules like ethanol play a crucial role in cooling the gas during this process, allowing it to condense more efficiently into protostars. It's a cosmic feedback loop. The very molecules that might one day seed planets with organic material are also midwives to the stars those planets will orbit. This discovery also hints at something extraordinary. The universe might be inherently primed for chemistry we associate with life. If clouds like Sagittarius B2 can brew alcohol and sugars in deep space, imagine what happens when those molecules hitch a ride on comets and asteroids, eventually landing on young, water-rich worlds. Every glass of wine or whiskey you've ever tasted contains atoms that might have formed in such a cloud billions of years ago, before our sun even existed. So while the idea of a drunken galaxy is amusing, the truth is far more exhilarating. These alcohol clouds aren't just curiosities, they're snapshots of the universe's relentless creativity, proving that even in the darkest voids, the ingredients for complexity and maybe even merriment are always simmering. Cheers to that! At first glance, Mercury seems like the last place you'd find ice, a scorched world where daytime temperatures soar to 800 degrees Fahrenheit, hot enough to melt lead. Yet hidden in the planet's polar craters, sheltered from the sun's relentless glare, lie vast deposits of water ice. This discovery turns everything we thought we knew about planetary extremes upside down, proving that even in the solar system's hottest neighborhood, cold traps can persist for billions of years. These icy sanctuaries exist thanks to Mercury's unique geometry. The planet's axis barely tilts, leaving deep craters near its poles in perpetual shadow. Without sunlight to warm them, these regions plunge to negative 300 degrees Fahrenheit colder than Pluto's surface. Radar observations from Earth first hinted at the ice in the 1990s, but NASA messenger spacecraft confirmed it in 2012, detecting bright reflective patches that matched frozen water's signature. Some of these deposits are dozens of feet thick, possibly delivering more water to Mercury than exists in all of Earth's deserts combined. Where did this ice come way out here? The leading theory involves a cosmic delivery service, comets and water-rich asteroids bombarding Mercury over eons, leaving behind traces of water molecules that migrated to the coldest traps. Solar wind could also play a role, with hydrogen particles from the sun binding with oxygen in Mercury's crust to form water. Over time, these molecules hopped across the surface like cosmic pinballs, eventually settling in polar shadows where they accumulated into icy reservoirs. What makes these deposits especially surprising is Mercury's lack of atmosphere. Without air to distribute heat, the line between sunlight and shadow becomes razor-sharp, creating temperature swings more extreme than anywhere else in the solar system. A single step from shadow into sunlight could mean leaping from Antarctic cold to furnace-like heat in an instant. This stark contrast allows ice to survive just millimeters away from blistering barren plains where no liquid water could ever flow. The implications stretch far beyond Mercury. If ice can endure on a world this close to the sun, it might lurk in unexpected places across the cosmos, hidden in lunar craters, buried on asteroids, or even nestled in the shadows of Venusian mountaintops. Future explorers could mine these deposits for drinking water or rocket fuel, turning desolate landscapes into pit stops for interplanetary travel. Mercury's icy secret reminds us that the universe rarely follows our assumptions and that clues to life's greatest necessities might be hiding in plain sight, or in this case, just beyond the light's reach. The moon may seem like a solitary sentinel in our night sky, but it's actually dragging an invisible comet-like tail behind it, a faint stream of sodium atoms stretching millions of miles through space. This ethereal feature, invisible to the naked eye, forms as tiny meteoroids constantly pelt the lunar surface, blasting sodium atoms into the void. Unlike Earth, which holds onto its atmosphere with gravity and magnetism, the moon's weak grip allows these particles to escape easily, creating a wispy trail that orbits ahead of and behind the moon as it journeys around our planet. Each month, Earth passes directly through this subtle lunar tail, though you'd never notice without specialized instruments. The sodium atoms don't rain down on us like cosmic glitter. Instead, they're funneled by Earth's magnetic field, concentrating into a faint, glowing spot in our upper atmosphere opposite the moon's position. Astronomers first detected this phenomenon in the late 1990s using sensitive cameras tuned to the specific yellow-orange glow of sodium. The effect lasts about 2 days as our planet glides through the densest part of the tail, turning Earth itself into a temporary screen for the moon's invisible artwork. What makes this tail especially fascinating is how dynamic it is. Solar wind and radiation pressure sculpt the sodium particles into a shape resembling a windsock blowing in a stellar breeze, narrow near the moon but fanning out dramatically downstream. During meteor showers like the Geminids or Perseids, when the lunar surface gets bombarded by extra debris, the tail briefly grows denser and brighter. It's a real-time demonstration of how even the gentlest forces can leave their mark on the cosmos, given enough time and the right conditions. This discovery reshapes how we see Earth-Moon interactions. Our planet doesn't just tug on the moon gravitationally, it also plows through its lingering traces, connecting the two worlds in ways far more intimate than simple orbital mechanics. Future explorers might one day use these sodium trails as navigational markers or even harvest them for resources, turning what was once an invisible curiosity into a practical tool. Until then, the moon's ghostly tail remains one of the solar system's quietest wonders, a whisper of atoms telling a story of perpetual bombardment and celestial ballet. Pluto may be small, but its days are anything but this distant world spins so leisurely. A single rotation takes 6.4 Earth days. That means if you stood on Pluto's frozen plains, you'd experience a sunrise that lingers for over 3 Earth days before twilight finally gives way to an equally drawn-out night. While Earth's 24-hour rhythm structures our lives, Pluto's sluggish rotation creates a calendar where the very concept of a week would feel absurdly compressed. What makes this slow dance especially intriguing is how it interacts with Pluto's wildly elliptical orbit. Unlike Earth's nearly circular path, Pluto's orbit stretches into a pronounced oval, bringing it alternately closer to and farther from the Sun over a 248-year cycle. This extreme orbit means seasons here aren't measured in months, but in decades. Imagine winters lasting over a century, where temperatures plunge to -400 degrees Fahrenheit, and nitrogen glaciers creep across the landscape like time-lapse rivers of ice. During its closest approach to the Sun, Pluto's thin atmosphere briefly thaws, creating a fleeting haze of nitrogen, methane, and carbon monoxide before refreezing as the dwarf planet retreats into the deep freeze. Yet even at its warmest, sunlight here is 1,000 times dimmer than on Earth, casting everything in an eternal twilight. The Sun itself would appear as little more than an exceptionally bright star in the sky, a far cry from the blazing disk we know. The contrast with Earth couldn't be starker. Our planet's relatively rapid rotation and axial tilt create a predictable rhythm of days, seasons, and years. But on Pluto, the very framework of time warps into something alien. A single Plutonian day spans more than 6 Earth days, while a year lasts nearly 2.5 centuries longer than the entire history of the United States as a nation. This glacial pace shapes everything on Pluto, from its weather to its geology. Frost patterns shift over centuries, not weeks. Ice mountains erode at speeds measured in millennia. Even the iconic heart-shaped Tombaugh Regio, likely made of frozen nitrogen, may only be a temporary feature on a world where change unfolds on timescales that dwarf human lifetimes. Yet there's a strange beauty in this extreme slow motion. Pluto forces us to rethink our Earth-centric notions of time, offering a glimpse into rhythms set not by our biology, but by the cold, patient mechanics of the outer solar system. It's a reminder that time, like gravity, is relative, and in the farthest reaches of our cosmic neighborhood, the clock ticks to a beat we're only beginning to understand. Black holes aren't just cosmic vacuum cleaners, they're messy eaters with terrible table manners. In 2018, astronomers witnessed something extraordinary. A supermassive black hole halfway across the universe, letting out a colossal belch of energy 100 million years after devouring a star. That's right, a black hole fart echoing across the cosmos, proving even these gravitational monsters can't digest their meals without some embarrassing cosmic indigestion. This delayed eruption came from a black hole in a galaxy 860 million light-years away, which had torn apart a star in a violent event called a tidal disruption flare. Normally, we expect black holes to fling leftover stellar debris outward immediately, like a kid hurling food they don't want. But this one held onto its meal for an astonishingly long time before burping out radio waves and X-rays like a cosmic afterthought. Scientists compared it to eating a heavy dinner and waking up with heartburn at 3 in the morning, except scaled up to galactic proportions. Here's what makes this discovery so revealing. Black holes aren't just silent traps where matter vanishes forever. Their magnetic fields and spinning accretion disks can trap and store debris in swirling holding patterns, like a messy kitchen where leftovers pile up for ages before getting tossed out. The belch itself was a jet of particles accelerated to nearly light speed, punching through surrounding gas like a champagne cork popping after the bottle's been sitting half empty for a century. But why the 100-million-year delay? One theory suggests the black hole's magnetic field lines got tangled during the feast, creating a storage system for energy. Over millennia, those lines finally snapped back into place, flinging the trapped material outward in a belated tantrum. Alternatively, the star's remains might have formed a temporary dam in the accretion disk, holding back the inevitable release until pressure overcame gravity's grip. This bizarre behavior challenges the textbook image of black holes as efficient destroyers. Instead, they're more like cosmic recyclers, stretching, spaghettifying, and occasionally regurgitating bits of their meals in ways we're only beginning to understand. Future telescopes might uncover more of these delayed eruptions, revealing black holes as dynamic, unpredictable diners rather than bottomless pits. So the next time you gaze at the night sky, remember, somewhere out there, a black hole might still be digesting a star it ate when dinosaurs roamed Earth, proof that in the universe, even destruction has its messy, time-defying quirks. What if everything around you, the chair you're sitting on, the screen you're staring at, even your own hands, was nothing more than an incredibly convincing illusion? The holographic principle, one of the most mind-bending ideas in modern physics, suggests exactly that. This radical theory proposes our three-dimensional universe might be a vast, complex projection of information encoded on a two-dimensional surface at the edge of space, like a cosmic version of those security holograms on credit cards, but scaled up to contain every star, planet, and atom in existence. The idea emerged from a surprising discovery about black holes. In the 1970s, physicist Jacob Bekenstein found that a black hole's entropy, a measure of its information content, is proportional not to its volume as you'd expect, but to its surface area. This hinted that all the information about what falls into a black hole gets compressed and stored on its event horizon like data on a celestial hard drive. Decades later, string theorists like Leonard Susskind and Gerard T. Hooft took this further, suggesting the entire universe might operate the same way. In their vision, the 3D world we experience could be a holographic projection from a 2D boundary we'll never see, like shadows on Pluto's cave wall written in the language of quantum physics. Imagine watching a 3D movie without glasses. The screen is flat, but depth emerges from how pixels interact. The holographic principle applies similar logic to reality itself. At its core, space-time may not be fundamental but pixelated at the Planck scale, about 10 to the power of negative 35 meters, with each pixel carrying bits of information. What we perceive as depth, texture, and solidity would then be emergent properties, illusions generated by how these bits interact. It's not that the universe is fake, it's that our experience of 3 dimensions might be a kind of cosmic user interface, simplifying unfathomably complex underlying data. This isn't just philosophical speculation. The holographic principle could resolve major tensions in physics, like the conflict between quantum mechanics and general relativity. In a holographic universe, gravity might emerge from quantum entanglement on the boundary surface, neatly bridging the two theories. Experiments with gravitational wave detectors and quantum computers are now testing predictions derived from this model, searching for telltale pixelation in space-time or anomalies in quantum correlations that could betray our universe's true two-dimensional nature. If proven, the implications would rewrite our understanding of existence. Consciousness, free will, even time itself might be secondary phenomena emerging from information processing on a flat, distant surface. Some interpretations suggest black holes could be glitches in this cosmic projection, regions where the illusion frays. Others propose that if we could decode the universe's boundary information, we might uncover hidden layers of reality or even the source code of physical laws. Yet for all its elegance, the holographic principle remains controversial. Skeptics argue its untestable metaphysics, while others counter that its mathematical consistency across multiple physics frontiers makes it too compelling to ignore. Whether our universe truly is a hologram may remain uncertain for decades, but the mere possibility challenges us to reconsider what real even means. After all, if reality is just an ultra-high-resolution projection, what does that make us? The observers, the dreamers, the ones trying to figure it all out? Perhaps we're not just inhabitants of the hologram, but active participants in its rendering. From diamond planets to black holes with indigestion, from stars older than the universe itself to moons that stretch your spine, we've journeyed through 30 cosmic revelations that shatter everything we thought we knew about space. Each of these facts isn't just a quirky footnote in astronomy. They're seismic shifts in our understanding, proving the universe operates on a scale of wonder and weirdness that defies human intuition. Who could have imagined a cloud of alcohol spanning light years, or a planet where storms hurl molten glass at thousands of miles per hour? These aren't sci-fi fantasies, they're real phenomena, each one a humbling reminder that reality outpaces our wildest imaginations. Think about the implications: the Great Attractor lurking unseen, dragging entire galaxies toward it like a cosmic riptide. The holographic principle, suggesting our 3D universe might be a projection from a 2D boundary we'll never see. Even time itself warps in bizarre ways, whether it's neutron stars spinning faster than kitchen blenders or black holes belching stellar remains 100 million years after their meal. These discoveries force us to confront a universe that's less a predictable machine and more a chaotic, evolving artwork, forever surprising us with new brushstrokes of physics. But here's the real kicker: we've only scratched the surface. For every mystery solved, a dozen more emerge. What's the true nature of Planet 9? Could the Methuselah star rewrite cosmic timelines? And what other secrets hide in the Boötes void's crushing emptiness? The more we learn, the clearer it becomes the universe isn't just stranger than we imagine, it's stranger than we can imagine. Now it's your turn. Which fact left you utterly stunned? Was it the water ice baking in Mercury's shadows or the moon's invisible sodium tail? Drop your pick in the comments. I'm dying to hear which cosmic truth blew your mind the hardest. And if you're hungry for more mind-bending revelations, hit that subscribe button. We've got a universe of wonders left to explore, and I promise you, the next batch of cosmic secrets will be even wilder. As we wrap up, remember this: every time you look up at the night sky, you're not just seeing stars. You're glimpsing an infinite puzzle, a tapestry of mysteries woven across billions of years. Somewhere out there, a sun sets in shades of blue over Martian dunes. A diamond the size of a planet glows in eternal twilight. A black hole hums a note too low for ears to hear. The universe doesn't owe us answers. It invites us to keep questioning, keep marveling, and above all, stay curious. Because the greatest discovery isn't any single fact, it's the realization that wonder never ends.